Welcome, everyone. Ready for another deep dive? Today we're tackling SFT Memorizes, RL Generalizes, a comparative study of foundation model post-training.
Ah, yes. This one really digs into a question that's been on a lot of researchers' minds.
Yeah.
Do these powerful AI models we're building truly understand, or are they just really good at mimicking?
Exactly. And the authors, Tianzi Chu, Yujiang Zai, Jihan Yang, and their team make a pretty compelling case for the power of reinforcement learning, or RL, in pushing these models towards actual generalization.
It's fascinating stuff, contrasting it with supervised fine-tuning, or SFT, and how that seems to favor rote memorization instead.
Right. Before we get lost in the weeds, though, quick recap for anyone just joining us. We're talking about foundation models here, those large language models, vision language models, the ones that have been making huge strides in the AI field.
Trained on massive data sets, they possess impressive capabilities, but there's always room for improvement.
And that's where post-training techniques come in, like taking a student with raw talent and then giving them specialized training to hone their skills.
This paper focuses on two specific approaches. SFT, which is kind of like memorizing flashcards, you feed the model labeled data, and it learns to connect specific inputs with the desired outputs.
Like a student cramming for a test.
Exactly. While RL is more dynamic, like training a dog with rewards and penalties, the model learns by trial and error, receiving positive reinforcement for good decisions and negative feedback for bad ones.
It's learning by doing, which intuitively feels like it would lead to a deeper understanding.
That's the hypothesis this paper is putting to the test.
And to do that, they designed two really clever testing environments, General Points and VIRL.
General Points is like a supercharged card game. Think of it as the classic Points 24, but amped up in complexity. The model has to use basic math operations to manipulate a set of cards and hit a target value.
Sounds fun, actually.
The cool part is it has both text-based GPL and vision language, GPVL versions, which lets the researchers test different types of generalization.
So they can tweak the rules to see if the model can adapt, and they can even change how the cards look, right? Like using different colors.
Exactly. Testing both rule-based and visual generalization.
Now, VIRL is completely different. It's a real-world navigation task. Imagine giving an AI model instructions to find its way through a city using landmarks and street directions.
That's a great way to test a model's spatial reasoning, how well it can understand instructions, and its ability to recognize visual cues in a complex environment.
And like General Points, VIRL has both text-based, VIRL, and vision language, VIRL, VL versions.
But they take it a step further. They test the models with absolute directions like north, south, east, west, and then relative directions like left, right, forward, backward. And to really test their generalization ability, they train the models in one city and then test them in a completely different city.
That's brilliant. So they're not just memorizing specific routes. They have to actually understand the underlying concepts of navigation.
Precisely. It's a multifaceted testing ground to see how well SFT and RL really promote generalization.
Okay, so we've got our contenders, we've got our arena. Let's get to the main event, the results. What did the researchers find?
Well, when it came to rule-based generalization, RL consistently outperformed SFT. The RL-trained models could apply the rules they'd learned to completely new rule variations in both General Points and VIRL.
It seems like RL enabled the models to figure out the underlying logic, rather than just memorizing specific solutions.
Exactly. And that trend continued when we looked at visual generalization. The vision language models trained with RL did remarkably well when the visuals changed. They could handle different card colors in General Points and navigate through unfamiliar cities in VIRL.
Whereas the SFT models struggled when the visuals changed, suggesting they were relying more on rote memorization.
Right. Especially in VIRL, where navigating a new city requires adapting to all sorts of new landmarks and spatial relationships.
So RL wins again. But what I found really surprising was the discovery that RL training actually improved the model's visual recognition abilities.
Right. That was an unexpected bonus. It seems that RL's focus on exploration and adaptation led to more robust and well-rounded learning, even boosting their perceptual abilities.
So it's not just about getting the reward, it's about developing a deeper understanding of the world.
Exactly. And this boost in visual recognition directly translated to their success in the visual generalization tasks. They weren't just memorizing patterns, they were learning how to use visual information for decision-making.
Okay, let's put some numbers to this.
Yeah.
In the VIRL mini benchmark, the RL-trained model achieved a whopping 33.8% improvement over the previous state-of-the-art.
Yep, and across the board, RL consistently beat SFT in terms of out-of-distribution generalization. The paper breaks down the performance differences for each task, and it's pretty clear that RL has the edge.
But hold on, it's not a complete knockout. The paper also shows that SFT still plays a crucial role.
Oh, absolutely. They found that SFT is essential for laying the groundwork for effective RL training. It helps stabilize the model's output format and makes it easier for RL to take over and fine-tune those decision-making capabilities.
So it's not SFT versus RL, it's more like SFT and then RL.
Exactly. A 1-2 punch for achieving optimal performance and generalization.
And they also found that more verification steps during RL training lead to better generalization.
Right, which suggests that allowing the model to reflect on its mistakes and adjust its approach is key to robust learning.
Makes sense. So lots to celebrate for RL, but the authors also point out a couple of open challenges that need more investigation. First, there's the puzzle of why SFT completely failed in the GPVL task.
Yeah, that was strange. Even with different settings and configurations, SFT couldn't get off the ground when visual input was added?
They think it might have something to do with how SFT handles the combination of reasoning and visual recognition in that particular task.
Maybe the abundance of reasoning tokens in the training data overshadows the recognition tokens, so SFT gets fixated on the reasoning and neglects the visuals.
Interesting. So maybe we need to rethink how we train these models when multiple types of information are involved.
Definitely worth exploring. The second challenge is about the limits of RL. It seems RL struggles when it starts with either a really weak SFT model or one that's already overfit.
So there's a sweet spot for the initial SFT model that maximizes RL's potential.
Right. If the SFT model is too basic, RL doesn't have a good foundation to work with. But if it's too specialized, RL might get stuck and not generalize well.
Sounds like finding that sweet spot is going to be crucial for future research.
Okay.
All right, now that we've covered the big picture, let's dig into the technical nitty-gritty of how they pulled this off. What did their setup look like?
Well, they chose Llama 3.2 Vision 11b. It's a powerful vision language model with 11 billion parameters, a solid choice for tackling the complexities of their tasks.
Definitely a heavyweight contender in the model world. And for the RL implementation, they went with the Proximal Policy Optimization Algorithm, PPO for short.
Ah, PPO, a favorite in the RL community for its stability and efficiency.
They basically treated the model itself as the policy network, so the model's outputs, whether it's text, equations, or actions, become the actions of this policy network.
It's an elegant way to unify the framework and apply RL to both language and vision language tasks seamlessly.
And then there's the verifier, which adds another layer of complexity to this setup.
Right, the verifier acts like a coach, providing feedback in the form of rewards and additional textual information to guide the model.
So it's not just a pass or fail, it's a here's what you did well and here's where you can improve kind of feedback.
Precisely, and that extra information is crucial because it helps the model understand the why behind its actions.
So in general points, if the model comes up with an invalid equation, the verifier would say something like, invalid equation, you cannot divide by 0, instead of just giving a negative reward.
And in VIRL, if the model takes a wrong turn, the verifier might say incorrect direction. The instruction was to turn left at the intersection, helping the model connect its actions to the instructions in the visual scene.
It's like having a personal tutor guiding you through the learning process.
Exactly. And then there's the sequential revision technique, where the input prompt dynamically changes over time.
So the model's not just working with the current state, it has access to a history of its interactions and the feedback it received.
It's like the model is having a conversation with itself, constantly updating its understanding based on the feedback it gets.
And the authors lay out the math behind this process, defining the input prompt at each time step as the combination of the initial prompt, previous outputs, and verifier feedback.
They even provide clear examples to show how this works in both general points and VIRL.
Now let's talk about the reward design. How did they incentivize the models to learn the desired behaviors?
Well, in general points, they kept it straightforward. The model gets a reward of 5 for generating a valid equation that hits the target value of 24.
And penalties for messing up, like using the wrong numbers, trying to divide by 0, or taking too many steps.
And importantly, in the GPVL version, they added a penalty for failing to recognize the cards in the image, ensuring the model was focusing on both reasoning and perception.
So it's not just about being good at math, it also has to see correctly.
Right. In VIRL, the reward structure is a bit simpler. The model gets 1 point for each correct action and loses a point for each incorrect action.
And again, they penalized the model for failing to recognize landmarks, emphasizing the importance of accurate visual perception in navigation.
They also streamlined the original VIRL design, removing the two-stage pipeline and online queries, making the training process more efficient.
So they really focused on the core challenges of instruction following, visual recognition, and spatial reasoning within the RL framework.
Absolutely. Now, how do we measure generalization performance? They used two main metrics: per-step accuracy and success rate.
Per-step accuracy is pretty self-explanatory. Did the model make the right choice at each step?
Right, and it's particularly useful in tasks like VIRL, where a sequence of correct decisions is needed to succeed.
Success rate, on the other hand, looks at the big picture. Did the model achieve the overall goal?
So in general points, it's about solving the puzzle, and in VIRL, it's about reaching the destination without errors.
The authors also go into detail about their statistical analysis, using binomial distribution to calculate error bars and Savitsky-Golay filtering to smooth the plots.
That level of transparency is commendable and ensures that their results are both robust and reproducible.
Now, I want to circle back to those ablation studies on GPVL, where SFT seemed to struggle. What did they find?
Despite trying different learning rates, freezing various prints of the model, and even giving SFT more diverse training data, including suboptimal trajectories with errors and feedback.
They were really trying to give SFT every advantage.
Right, but SFT still kept falling back on memorization rather than generalization, even with all those tweaks.
It almost suggests that memorization might be inherent to how SFT learns, regardless of the data it's given.
It's an interesting observation that highlights the potential of RL for tasks that require true understanding and adaptability.
Okay, let's dive a bit deeper into the mathematical side of their RL implementation. What's the framework they used?
They use a standard RL setup with clear definitions of the state space, action space, reward function, and policy network, all seamlessly integrating LLMs and VLMs into the RL pipeline.
And their explanation of the sequential revision process is really well laid out, with the mathematical definition and illustrative examples.
They even analyze the computational costs, estimating the FLOPs for both SFT and RL, giving us a good understanding of the computational trade-offs.
I was particularly intrigued by their great experiment with using suboptimal trajectories as training data for SFT.
That was clever. They wanted to see if exposing SFT to those errors and feedback during training would improve its generalization ability.
It's like they were trying to teach SFT to learn from its mistakes.
Exactly. But even with this tough love approach, SFT still leaned towards memorization, further supporting the idea that it might be a fundamental characteristic of SFT.
Now, their description of the training pipeline is quite detailed, starting with SFT initialization and then scaling up the compute separately for both SFT and RL.
And they ensured fair comparisons by using a shared learning rate for each experiment, which adds to the rigor of their study.
Okay, so they've laid out this amazing study with compelling results, but as with any research, there are always limitations and open questions that point towards future research directions. What are some of the key takeaways in that regard?
Well, one of the most puzzling findings was the complete failure of SFT in the GPVL task when visual input was introduced.
It seemed like no matter what they tried, SFT just couldn't handle that combination of reasoning and visual recognition.
They speculated that the imbalance between reasoning and recognition tokens in the training data might be the culprit, with the reasoning tokens dominating the learning process.
So SFT might be getting so focused on the reasoning aspect that it neglects the visual information.
It's a fascinating hypothesis that highlights the importance of understanding how these models process different types of information.
And then there's the issue of RL's performance being sensitive to the initial SFT model.
Right. If the SFT model is too weak or too strong, RL doesn't seem to perform as well.
Finding that sweet spot for initialization seems crucial for maximizing RL's potential.
It's like finding the right balance between pre-training and fine-tuning to achieve optimal results.
These limitations and open questions are just as valuable as their findings because they guide us towards new avenues of research and deeper understanding.
Absolutely. They highlight the complexities of foundation model post-training and the ongoing quest to develop truly intelligent systems.
It highlights the need to strike that delicate balance where the SFT model provides a solid foundation without being so rigid that it limits RL's adaptability.
Exactly. It's an area ripe for further research, finding that optimal starting point for RL. And that hypothesis about SFT's failure in GPVL, that's really intriguing.
Yeah, the idea that too many reasoning tokens might be drowning out the recognition tokens. causing SFT to prioritize reasoning over visual processing.
It makes you wonder if we need to reevaluate how we structure training data for these multimodal tasks. Maybe we need a more balanced representation.
Perhaps some kind of weighting system to ensure one type of information doesn't completely overshadow the other during training.
It's definitely a question worth exploring. These limitations and open questions, they're not just setbacks, they're opportunities for pushing the field forward.
They reveal the intricacies of foundation model post-training and the challenges we face in developing truly intelligent AI systems.
Couldn't agree more. It's at the edges of what we know that we often find the most exciting new discoveries. Thinking big picture for a moment, what do you see as the broader implications of this research?
Well, I think it underscores a crucial shift in how we think about AI development. It's not just about building models that can memorize, it's about fostering true generalization.
And RL seems to be a key player in making that happen, moving away from rote learning and towards systems that can adapt and learn in a more human-like way.
Absolutely. It also raises the bar for how we evaluate these models. Standard benchmarks might not be enough anymore.
We need to challenge these models with tasks that require genuine understanding, adaptability, and problem-solving skills they haven't explicitly been trained for.
This paper has been a real eye-opener in that regard. It's pushed the boundaries of our understanding and set the stage for exciting new research directions.
It's a testament to the power of RL in shaping the future of AI, and it's really inspiring to see these kinds of advances being made.
It's been a fantastic deep dive, and I really appreciate you joining me to explore this groundbreaking work.
The pleasure was all mine. Until next time.